Welcome everyone. We started part 3 of this lecture 2, basic convexity 4, page 23 of your handout slides. We claim that if, here we claim if S is a set of a point, X belongs to n-dimensional Euclidean space, subject to AX equals to B, and X is non-negative. And D is a direction of X if and only if D is not equal to 0, D is greater than 0, and A times D equal to 0. So this part, we're going to prove both direction. So either first we're going to assume if this direction D is satisfy this set of condition, D is not equal to 0, D is greater than or not equal to greater than or equal to 0, and A times D equals to 0, and then D is a direction. So what is the direction based on the definition of the ray we just talk about last end of the last slide? The ray is particular vertices of ray and the direction of the ray. So basically means for y is representing all the point that starting from x naught go all the way along this direction D with any positive amount of scale. So let's take a look how to prove that. We decided to prove the reverse direction first. So it's first assuming D satisfy the conditions D is greater than or equal to 0, not equal to 0, and A times D equals to 0. So based on the definition, we also want to see if for each one of x naught belongs to S, belongs to this condition, we must show that starting from this vertices, all the ray starting from that vertices and belongs to S as well for all the u greater than or equal to 0, all the positive non-negative u. So we can easily first show that A times x naught plus u times D equals to B, actually, if we satisfy the first constraint, okay? X naught plus u plus D, x naught plus u times D is non-negative for all the non-negative u. Okay, so therefore we can show that x naught plus u times D belongs to S for all the non-negative u. So we expanded this portion, A times x naught, okay, plus u times A times D equals to B times plus u times 0, because A times D actually equals to 0 based on the assumption. Okay, so then we can make sure that A times x naught plus ud is equal to B exactly. So satisfy the first constraint. Second, since D is greater than 0, non-negative, greater than or equal to 0, and also x naught belongs to the S, so x naught is also greater than equal to 0. So x naught plus u times D, so it's a non-negative plus a non-negative times non-negative, of course, is greater than equals to 0. So therefore, we prove that x naught plus u times D belongs to S because satisfy both conditions right here. So that's the first part, reverse direction. So first we're going to, next we're going to show D is the direction, assuming D is the direction of S, and D has to satisfy this condition. So first, if a D is the direction of S, by definition, and D is not equal to 0, and for each one of x naught within S, we have A times x naught plus u times D equals to B, x naught plus u times d is greater than or equal to 0 for all the non-negative u. So therefore, b equals to a times x naught, okay, plus u times a times d, okay. So this part equals to b, a times x naught equal to b. So therefore, and u is not necessarily 0, but can be a positive value. So therefore, a times d equal to 0. Okay, so u can be any value in that case. Also, x naught plus u times d is non-negative. For all the u is non-negative. Therefore, d has to be non-negative because this part is non-negative, u is non-negative, and if we want this always to be true, d has to be non-negative. So therefore, we're proving if d is the direction of s and d satisfy all three conditions over on the right hand side. So this is easily proof, and we call it construction method, and this is also referred as the so-called forward-backward method. We're going to talk about later on. And it's very straightforward, not too much trick. All we have to do is using one side of this if and only if condition as a starting point, see if you can reach the other side. So we prove the reverse direction first, then proving the forward direction. Okay, now let's introduce the concept of an extreme direction. A direction D is a convex of a convex set S is called a extreme direction if this direction cannot be represented by two distinguished directions in this set S. So what it says is D cannot be represented as D1 or D2 of S as a cone combination of the D1 and D2. So there's no way I can using, if D is an extreme direction, there's no way I can using two distinguished direction from S and using the cone combination to represent the D. So any ray whose direction is an extreme direction is called extreme ray. Take a look. This one. For the standard Cartesian space, E1 and E2 is the univectors of x1 and x2 dimension. Any D can be represented by the cone combination of E1 and E2. Second, if you look at this, this is the feasible area. D1 and D2 are extreme direction of this cone, and then anything D can be represented as two different D1, D2, their cone combination. Cone combination means U1 and U2 can be any positive number, so it can be any of the direction in this purple area. All right, so next we'll talk about convex cone. A convex set C is called a convex cone if we find any point belongs to this convex cone, and u times x also belongs to this convex cone for whatever u is non-negative. Note that each cone contains the origin of the point of origin, and each cone contains at least one ray with a vertex at the origin point. So for any D equals to the cone combination of D1 and D2, and U1 and both U1 and U2 are non-negative, any ray whose direction is a extreme direction is called extreme ray. So this is the same concept we had. Okay, so for example, B can be represented as a cone combination of A1 and A2, but B prime outside this cone cannot be represented as the cone combination of A1 and A2. So this is what we're talking about. Next, the convex cone remark. Giving a set of vector in n-dimensional Euclidean space, A1 through AK, Okay, the set S for y belongs to E sub n, y equal to the cone combination of all the vector a1 to ak for uj is non-negative, is a cone is said to be generated by a1 through ak, the so-called the cone combination. We already talked about this. The illustration like this, we could have a1, a2, and a3 as spending in E sub n, but not necessarily all of them are required. But we have a so-called two extreme point, A1 and A3. Any point within this cone, okay, we got a cone combination, within this cone spanned by this yellow dot line, B, for example, represented by AX equals to B, at X is greater than 0. So X in this situation is the direction of that, okay? The cone combination of that. So B is the elements of a cone generated by A1 through AK. So we talk about this concept a little bit later as part of a linear programming's constraint set and how that's going to be used in the solution space. So basically your right hand side is a cone combination forming by the rows of your constraint matrix. Next, we're going to introduce a very popular concept and very important one called convex or concave function. Before we introduce a so-called convex set, it's a set of data point, we call it point set, a set of point as forming a convex area regions or non-convex region, taking a convex combination of any point within that set still belongs to the set. But now we're shifting our attention to the function itself, giving a set S belongs to n-dimensional Euclidean space with the f of x defined for all the x inside the set S. The function f is convex if for any 2 point x1 and x2 belong to S, for any u is between 0 and 1. Let's take a look. For example, all right, so here we have a x right here, horizontal, and y-axis is the value of f of x. Look at the left-hand side of this equation. If I take any 2 point within this S, which is x1 and x2, okay, any point between them called x, for example, and x belongs as a so-called convex combination of x1 and x2, so u times x1 plus 1 minus u times x2, which is this point right here, okay, which is this point right here, okay? And then we have two different possibilities, and this is the function in the yellow line. And here is, we can see that actually we're plugging x into this function, we're getting this equation, this functional value. So that's the left-hand side. If I plug in the value of x, which is a convex combination of x1 and x2, which we get this level, okay? However, I can also using a convex combination of its f value. So here I have a f of x1, here I have f of x2, f of x2, f of x1. Plugging x1, I get this value. Plugging x2, I get this value. And then do a convex combination of that, which is what? The value on this line in between. So that's the u times f of x1 plus 1 minus u times f of x2. And this point has always going to be higher than the original function u. Sorry, I made a typo right here. Actually, this value, which is f of u times x1 plus 1 minus u times x2, should be less than below this u times f of x1 plus 1 minus u times f of x2. So this is the convex function definition. However, the second function, if the point we plug in x on this function, which is the left-hand side, if it's greater than the line segment between these two f of x, then if they're always higher than this point, and then this is a concave function in that regard. Sorry about the typo, but correct that. Next, we take a look at some special condition. The linear function is both convex function and both concave function as well. On the right-hand side, neither the convex nor concave function, if this is like function like that on the right. This slide talks about polyhedral set. A polyhedral set is set S is called polyhedral set if it's an intersection of a finite number of half spaces. Okay, we talked about half spaces already, which is if you can find a so-called hyperplane and half of space is either below or above this hyperplane. So if it's forming by an intersection of this set of hyperspace, we call the hyperplane, and here illustrated as the edges. Okay, on here, do the edges from here, and basically this is the intersection of all the half space. If it's equal, and that's the represent this plane, and less than equal or greater than equals is the half space, which is formally saying a times x is less than equals to b, is also a linear inequality constraint of a combination or intersection of a whole bunch of half spaces. Okay, and also the set S is called a polyhedral cone if the S is the intersection of a finite collection of half spaces whose hyperplane passes through the origin. So if all these hyperplane passing through the origin and the intersection part of of all these half spaces and forming a so-called polyhedral cone, which is the pink area I illustrated. And the shadow area represents which part of the half space on this supporting hyperplane and defining this polyhedral cone. All right, so this one is to just illustrate how to represent a so-called convex combination of a point within this region using its corner point or boundary point. So y hat, which is 1, 1, equal to 1/2 of 1, 2, and 1/2 of 1, 0, which is this one and that one. And 1, 2, this data point is also can be using a convex combination between 0, 2, and 2, 2. Same thing. 1, 0, it can be represented as a convex combination of 0, 0, and 2, 0. Okay. Combine these together, the y hat can be represented as a 1/4 of 0, 2, okay, 1/4 of 2, 2, 1/4 of 0, 0, 1/4 of 2, 0. So we can always using its extreme point to represent any point within this region defined by this extreme point. Next is the important concept we call the polyhedral theory. Let's take a look at this theory. Okay. The set S defined by an x belong to n-dimensional Euclidean space is actually the vector dimension of this x. Ax equal to b and x is non-negative, is non-empty and bounded, contain finite number of radius, polyhedral set. So what does that mean? Which means we don't have these open area for now. Okay. But also a collection of all the extreme point of x, x1 through xk, x1 to sk over here, is a finite and non-empty. So this area within is finite and non-empty. X belongs to S, therefore, if and only if x can be represented as a cone combination of x's, and also summation of ui equals to 1, and we'll call a convex combination of all the extreme point within. All right. So this is the first part. If the boundary is bounded, the boundary is closed, which you call it bounded, and this is any point within can be represented as a convex combination of all the extreme points. This may not be unique because all the x1, x2, x3, and x5, and they are not linearly independent. So we can choose, for example, x can be represented as a convex combination only defined by x1, x4, and x3, and it can be also using x2, x5, and x3 to define x. Okay, so if the extreme point of the polyhedral is higher than the dimension itself, which is the n dimension itself, and then the convex combination is not unique. This is a little bit different from the concept of defining a basis of an n-dimensional Euclidean space. The next concept we want to introduce is, even though the the feasible region, okay, the polyhedral set region is not closed, we want to show next is any point within this open region can be represented, for example, x right here, can be represented as the convex combination of the extreme point. Extreme point will be x1, x2, x3, x4 right here. Can be represented as a convex combination of the extreme point plus the cone combination of their extreme direction. Here we have is d1 and d2. So we parallel moving the d1 here, parallel moving the d1 here and d2 here, the blue line, and the cone combination can be represented x anywhere inside this cone. Okay, take a look. Let the set S is x belongs to n-dimensional Euclidean space, ax equal to b, x is greater than equal to 0, and there's a polyhedral set, a set of extreme point called E, and a D is a set of extreme direction of S. E can be more explicitly x1 to xk is not equals to empty set and it's finite. So we'll have a finite number of extreme point, and D is equal to, if D equals to empty set, then S is bounded. If D is unbounded, S is unbounded, if the D collection, extreme direction, is not equals to empty set. But it's also finite. So now we say any point belong to S is right here, there exists a uj great non-negative, and mu I is non-negative. Any x belong to the set S can be represented as the convex combination of the extreme point plus the cone combination of the extreme direction. So here, in order to define it as a convex combination, so the summation of uj equals to 1, but I don't have a restriction on the mu I. The mu I just has to be non-negative. So this is the same illustration I have. Any point x, okay, on here, any point x on here can be represented as the convex combination of the extreme point. First we got the extrem right here as your vertex of the ray. Then we migrate D1 and D2 into the blue line right here, and then using the cone combination to reach, define the final point x. All right, so this is a polyhedral set theory, basically saying doesn't matter your the set S is bounded or unbounded, okay, which means if you have extreme direction or not. We call that if there are extreme direction exists, which this set is not empty set, then it's unbounded. If the extreme direction set is equals to empty set, then S is bounded. But anyway, any x within this feasible region can be represented as a convex combination of extreme point and the cone combination of extreme direction. So here for the minimization problem was minimize C transpose times X, subject to X belong to the set S, which is a polyhedral set, given D1 and D2 are the two extreme points of the X feasible region. Let's take a look at the relationship. First relationship is if the C is the cost coefficient factor, the dot product between C and all the DJs, D1 and D2 in this case, two extreme direction here, their dot product equal to 0 for some DJ, then C has the same direction as one of the DJ. Then you have a so-called multiple optimal. So in this case, all the red line up here representing the possible optimal error, because in the minimization problem, you pushing the reverse direction of the C, which is a negative C direction. When you keep pushing, and since this is also perpendicular to D1, therefore your optimal solution will be on this, along this D1 direction. Okay, that's the first condition. Since we're minimizing, so we're going pushing the objective function towards the reverse direction of the C. Let's look at the next example. If the dot product of C to DJ, which is any one of them, forming an acute angle with all the DJs, and then you have a finite number or a finite optimal solution, unique finite solution. Why is that? Because we pushing the reverse direction of the C, therefore anything along this two extreme direction will not matter, and your optimal solution could be one of these corner point defined by the boundary region. And this unbounded region does not affect you because we're pushing the reverse, opposite direction of D1 and D2. That's the second condition. So the third condition is if the dot product of C to some of DJs are less than or equal to 0, which is C and D, all these are forming obtuse angle, and then you have an infinite or unbounded optimal solution. Again, if we're pushing towards the negative reverse direction of C, since we're minimizing it, so we're pushing this direction, and this direction we can push all the way to infinite number large of the direction. So it depends on, so now we're using this particular slide to introduce the relationship with your coefficient vector to all the extreme direction in your feasible region defined by S. Okay, this is a very important theory. Just using illustration to show you why this is like that. And we're using this property very big. And here you can see fairly straightforward why this is work like that. But we're going to use this property later on to prove many other proposition and theorem based on this to determine the outcome of your linear program has what type of a solution. Okay. Polyhedral set is almost repeat. If X is bounded and non-empty polyhedral, as right here, there exists at least one optimal solution. Okay. Next, the theorem says, let's find the Z star equals to the minimize of a C transpose X subject to A times X equals to B, and X is non-negative. Then there are two conditions. First, Z star is your optimal objective function value could be greater than negative infinity, which means you have a finite objective function value. Otherwise, we call it infinite negative infinity, which is unbounded solution. So that means your optimal objective function value is bounded. Okay, is it bounded? If and only if the C transpose times dj is greater than or equal to 0 for all the dj. So this is basically this condition in the middle. Okay, if C times dj for all the dj's equals to 0. Second, left hand side is the same thing. The optimal objective function value is bounded. For some extreme point, optimal feasible solution. So some of the extreme point solution, basically these two says the same thing. Okay. So first we're going to using the polyhedral theory to prove this. For example, the set of feasible regions right here, okay, can have K of extreme point and L of extreme direction. If AX equals to B and X is non-negative, then there exists a Uj and mu I so that X equals to the convex combination of Uj and cone combination of D, which is convex combination of X and cone combination of D, which is extreme direction point at extreme direction. We have additional constraint on summation of Uj is equal to 1. Okay. We can actually forming an equivalent linear programming problem which minimizes Z based on the convex combination of C transpose times Xj, which is using all the J are the extreme point, and the cone combination of extreme direction. So here what we have in the subject to summation of Uj equals to 1, and Uj and mu I are non-negative. However, since this is a minimization problem, and we know that C transpose times D based on the definition is greater than equal to 0. So this part is greater than equal to 0, and mu I are greater than equal to 0 as well. So if there's any positive value of C transpose times DI, then this part will deteriorate my objective function. So since we're minimizing, we basically eliminate the second part. So mu I is all equal to 0 at all the optimal solution. So therefore, it's only the optimal solution be only defined by the convex combination of your extreme point in that sense. And that means also the extreme direction are not doesn't matter in this particular case because all the UIs are going to be equal to 0 at the minimize point. If C transpose times DI, which is this part, is less than 0, so using positive mu I will actually improve my objective function. Then we can make the Z, which is my objective function value, as small as possible, and therefore we define this type of problem is a so-called have an unbounded solution. Next, part B. The same theory, just part B focused on here, okay? So if we have a finite objective function value, then some of the extreme points actually are optimal feasible solution. So let's take a look. Assuming C transpose times DI greater than 0 for all the J's, or the I's actually, the cos vector forming a Q angle with all the extreme direction. This is simply the problem becomes, and the equivalent linear programming problem, just like we said it before, and the second part define the extreme direction are not going to be matter. So remember, there exists a extreme point xk, which are the one of the optimal is the optimal feasible solution. We'll call this xk. So for example, we define the xk is that optimal. So C transpose times xk is less than or equal to all the other extreme point in this feasible region S. So we can write it that way. C transpose times xj and uj is basically a convex combination of the optimal the solution is greater than, since it's not optimal, greater than if I replace all of them by C transpose times xk. Okay, since all of them has a C transpose times xk, I can take it out of the summation. So it will be C transpose times xk times summation of mu j, uj, and uj is what? Based on our constraint has to be equal to 0, equal to 1, I'm sorry. And so therefore the whole thing equal to C transpose times xk, and which is the optimal solution. So that means that the xk is the optimal feasible solution, and Z star equal to C transpose times xk. All right, so this is fairly straightforward. Let's review this real quick. A transpose A times X equal to B, and the rank of the A matrix equal to M, which is, we usually refer the A matrix is full row rank. We can separate or partition this A matrix into a square matrix in the first, since this is a full row rank. So we're finding M of the linearly independent column to form B, and the rest of a column to call N, times X is an N by 1 vector. So B is an M by 1 vector, the rank of A is M. So also we can separate the X into XB and XN. So XB corresponding to the column in the B matrix, XN corresponding to the variable in the M matrix. So we can partition this, and A times X equal to B can be rewrite it as a B times XB plus N times XN equals to B. If we forcefully set the XN equal to 0, therefore B times XB equals to right hand side B. And we can also directly calculate a particular solution. Here in linear program, we call it basic solution, XB, and XB are referring to the basic variable equals to the value of B inverse times B. Okay, we can directly using linear algebra to calculate that. So every basic solution is B inverse times B as a basic portion. All the non-basic portion are 0, and this we'll call a basic solution. If a basic solution is satisfy the non-negative constraint, we call it basic feasible solution. Many times later on you see that we call it BFS. So basic feasible solution if B inverse times B is non-negative. Okay? And also, if the current solution is called non-degenerate basic feasible solution, if all the entries in all the basic variable taking a positive value. If you have a sum of the basic value variables and the current value is equal to 0, and then we'll call it a degenerate solution. Okay. So that means even if we can find two separate B bases, create exactly the same solution, B hat inverse times B equals to B inverse times B, and then even we change the basis, change the column, and we have a degenerate solution. And that also many times means the row rank of A is not M, is less than M. In reality of application, many times we refer this thing happen, we call that we have a redundant constraint. Okay. Next, I'm going to using a different next video to explain the rest of this lecture. I'm going to stop right here. We'll see you in the next video.